Dear friends, now we are going to discuss about that estimation techniques of angle of arrival. So here we have listed out that many types of AOA techniques. So in that, the first thing is Bartlett AOA estimate. So if the array is uniformly weighted, we can define the Bartlett AOA estimation. So if the array, that antenna array is uniformly weighted, so we can estimate using of this Bartlett AOA estimation. So here, the pseudo spectrum of that particular theta for that Bartlett AOA estimation is a power of h of theta and r excess of a of theta. So the Bartlett AOA estimate is the spatial version of an average periodogram and is a beforming AOA estimate. So under the condition where this S bar, that means S vector represent that uncorrelated monochromatic signal. So that S vector is nothing but uncorrelated monochromatic signal. And there is no system noise we are considering here. So for that, the equation how we are representing, see here, this is the formula for Bartlett estimation. So now the post spectrum of theta is equal to modulus of summation of I is equal to 1 to d and summation of m to 1 to m e power j m minus 1 kd sin theta minus sin theta I, the modulus of square. So now this periodogram is that equivalent to spatial finite Fourier transform of all arriving signals. So how to calculate this periodogram is, so normally if you are calculating the Fourier transform, that means especially spatial finite Fourier transform for all the arriving signal, so that is the equivalent to this periodogram. So this is also equivalent to adding all beam steered array vectors for each angle of arrival and finding the absolute value square. This is all equivalent to adding all beam steered array vectors for each angle of arrival and finding the absolute value square. So now for this BOA estimation, we got this waveform. See here, so this is the BOA Bartlett estimation for angle of arrival. So in that angle values from minus 20 to 30 we are mentioning here. So based on that, the post spectrum of theta value has occurred. So now the next thing is, this is the another example of Bartlett estimation. So in that Bartlett spectrum, you can see this theta value from the first picture we have discussed, the theta one from minus 10 degree to 10 degree. Now here the second example is the theta post spectrum value is minus 5 degree to 5 degree. So these are the examples of Bartlett estimation of angle of arrival. Next, followed by, we are going to discuss that Capon AOA estimation. So, this Capon AOA estimate is known for minimum variance distanceness response. So, that simply we call as MEDR. It is alternatively no maximum likelihood estimate the power steering from one direction while all other sources are considered as interference. So thus the goal is to maximize the signal to noise ratio while passing the signals of interest undistorted in phase and amplitude. So the source correlation matrix RSS is assumed to be diagonal. So the maximized SR is accomplished with a set of array weight. So W is equal to W1, W2 and Wm. So now this Capon AOI estimation. So how to define the equation? See here. Post spectrum for first spectrum of the theta is equal to 1 divided by AH of theta r excess of minus into a power of theta. So it is clear that Capon AO estimate has much greater resolution than the Bartlett angle of arrival. So in that case, where these competing sources are highly correlated, the Kappan resolution can actually become worse. So now the derivation of that Kappan weights are conditioned upon considering that all other sources are interference. So if the multiple signal can be considered as multipath signal, the relay amplitude and the uniform space, then the uncorrelated condition is met and the Kappan estimate will work. So the advantage of Bartlett and Kappan estimation method, there are non-parametric solution and one does not need a prior knowledge of specific statistical properties.